Welcome to this presentation. You are watching Vlsi Design Lecture Series. Today we are going to speak about power and speed trade-off in data path structures. We have seen already that the adders, multipliers, shifters, which are explored the trade-off between the speed and the area and ignored the power consideration. Now let us analyze the third dimension of the design exploration space. Since most of the approaches to minimize power they are considered here, typical digital designs are either latency or throughput constraint. A latency constraint design has to finish computations by a given deadline. Interactive communication and gaming are examples of such. Throughput constraint designs, on the other hand, must maintain a required data throughput. So, a 1000 base T gigabit Ethernet connection has to maintain a constant throughput of 1 gigabit per second. The architectural optimization techniques that are available to the designer differ based on the design constraints. Pipelining or parallelization, for instance, works effectively for the throughput constraint scenario, but it may not be applicable to the latency constraint case. With the fixed architecture of the data path, speed, area, and power can be traded off through the choice of the power supply voltages, transistor threshold, and device sizes. So, this opens the door for a large variety of power minimization techniques. And now let us see one by one. And the first category is enable time. Some design techniques are implemented or enabled at design time. Transistor width, length, for instance, are fixed at the time of design. Supply voltage and transistor threshold, on the other hand, can be either statically during the design phase or changed dynamically at runtime. Other techniques primarily address the time that the function or model in a digital design is in idle mode. It is only logical to require the power dissipation of a mobile in sleep mode should be absolutely minimum. And the next one is targeted dissipation source. So another classification of power management techniques concerns the source of power dissipation they address, that is the active power or leakage power. Lowering the supply voltage, for example, is a very attractive technique. It not only reduces the energy consumed per transition in a quadratic way, and but also reduces the leakage current. On the other hand, increasing the threshold voltage mainly impacts the leakage component. Here you can see the active and the leakage time for the constant throughput and variable throughput latencies. In design time, the lower VDD, multiple VDD and transistor sizing and logic optimization can be done in design time. In sleep mode, clock gating can be utilized to reduce the power minimization, power consumption. And in runtime, dynamic voltage scaling can also be used. Similarly, for leakage also. In design time, multiple threshold voltage can be used and active techniques can be employed. Whereas in sleep mode, sleep transistors are used and variable VTH is also used, and variable VTH active techniques can also be used at runtime. So the sleep mode of operation deserves for special attention. If a digital block receives a clock while in idle mode in clock distribution network, together with the attached flip-flops, and continues to consume energy even when no computation is performed. So you can recall that typically 1/3 of the total energy of a digital system is consumed in a clock distribution network. A common method to reduce the power in idle mode is the clock gating technique introduced, which is in the later 1980s. In this approach, the main clock connections to a model is turned off whenever the block is idle. However, clock gating doesn't reduce the leakage power of the idle block. So more complicated scheme to the lower the standby power have to be used, such as increasing the transistor thresholds or switching off the power rails. And now let us focus on the design time power reduction techniques. And the first method is reduction in supply voltage. That is, reduction in supply voltage result in quadratic power savings, and thus is the most attractive approach. On the negative side, the delay of the CMOS gate increases inversely with the supply voltage. At a data path level, this loss of performance can be compensated for by other means such as logical and architectural optimizations. For example, a ripple carry adder can be replaced as a faster structure such as look ahead adder, and the latter implementation is larger and more complex, which translates into a larger physical and switching capacitance. This is more than the offset by the fact that the faster adder can run at a slower supply voltage for the same performance. The trade-off between the ripple and look-ahead operates at the logic level. Similarly, even more effectively, architectural optimization can be employed to compensate for the effect of the reduced VDD. And the supply voltage that cannot be reduced any further because no extra delay can be tolerated. So we use this topology at reference data paths for our study and present power improvement numbers with respect to this reference. So the average power consumed by the reference data path will be P reference is equal to C reference into V reference squared into F reference, where C reference is the total effective capacitance being switched per clock cycle. The effective capacitance can be determined by averaging the energy over a sequence of random input patterns with a uniform distribution. And one way to maintain the throughput while reducing the supply voltage is to utilize the parallel architecture. And two identical adder comparator data paths may be connected in parallel, allowing each unit to work at half the original rate while maintaining the original throughput. Since the speed requirements for the adder and comparator and latch have decreased from 25 nanoseconds to 50 nanoseconds, the voltage can be dropped from 5 volt to 2.9 volt, and the voltage that doubles the delay. While the data path capacitance has increased by a factor of 2, the operating frequency has correspondingly decreased by a factor of 2. Unfortunately, there are also a slight increase in the total effective capacitance due to the extra routing and data multiplexing. This results in increased capacitance by a factor of 2.15. So the approach presented trades-off area for power as the resulting area is approximately 3.4 times larger than the original design. This technique is only applicable when the design is not area constrained. Furthermore, parallelism introduces extra routing overhead which might cause additional dissipation, and careful supply voltages and careful optimization is needed to minimize this overhead. Parallelism is not only the way to compensate for the loss in performance. Other architectural approaches such as the use of pipelining can also be accomplished for using the same goal. The most important message in the preceding analysis is that if the power dissipation is the prime concern, dropping the supply voltage is the most effective means to achieve the goal. The subsequent loss in performance can be compensated if necessary by an increase in area within certain bands. This is accurate since the area is no longer the compelling issue, and it is used due to the dramatic increase in integration levels of the loss decay. And the next concept is using multiple supply voltages. Reducing the supply voltage is fairly straightforward, but it may not be optimal. So reduced supply evenly lowers the power dissipation of all logic gates while evenly increasing their delay. A better approach is to selectively decrease the supply voltage on some of the gates. For those which correspond to fast paths and finish computation early, and those with gates that drive large capacitances have the largest benefit for the same delay increment. And this approach, that is using multiple supply voltage, however, requires the use of more than one supply voltage. Multiple supply voltages are already employed frequently in today's ICs. A separate supply voltage is provided for the I/O for compatibility reason, where the I/O ring is designed with the transistors with the thicker gate oxides to sustain higher voltages. The logic core is powered from lower supply voltages and uses transistors with thinner oxides. And this approach can be extended to lower the power dissipation of the circuit. For instance, every module could select the most appropriate voltage from two or supply options. Even more example, multiple voltages can be assigned on a gate by gate basis, and you can consider, for instance, the digital system, which consists of a data path clock with a critical path of 10 nanoseconds and control block with a much shorter critical path of 4 nanosecond, operating from the same supply voltage of 2.5 volt. And also assume that the data path clock has a fixed latency and throughput, and that no architectural transformations can be applied to lower the supply. Since the control block finishes early, its supply voltage can be lowered. A reduction in VDDL, that is equal to 1 volt, increases its critical path delay up to 10 nanosecond and lowers its power dissipation by more than 5 times. We effectively exploit the discrepancy in the critical path length of the various models to selectively lower the power consumption of the models with larger slack. And combining multiple supply voltages on a die, level converters are required whenever a module at the lower supply has to drive a gate at the higher voltage. If a gate supplied by VDDL drives a gate at VDDH, then the PMOS transistor never turns on, and resulting in a static current and reducing output swing. A level conversion performed at the boundaries of the supply voltage domains prevents these problems. An asynchronous level converter based on DVSL template similar to the low swing signaling gate, and the cross-coupled PMOS transistors perform the level conversion by using positive feedback. So the NMOS transistors operate at a reduced overdrive, and they have to be made large to be able to overpower the positive feedback. For a low value of VDDL, the delay can become very long. So due to the reduced overdrive, the circuit is also very sensitive to variations in the supply voltage. Thank you.